Assalamualaikum everyone. I am Sara Javed and welcome back to the channel Data Science Explorers. If you've ever wondered how data science can help us understanding and predict the value of everyday items. So today we are kicking off an exciting new series where we will build a powerful laptop price prediction model from scratch. In this first part, our mission is to dive deep into our laptop dataset. We will explore its structure, cleanup, and messy data, and most importantly, introduce some brand new feature that will make our prediction model super accurate. Think of it as laying the groundwork for a skyscraper, a strong foundation key. So let's get started. Firstly, data loading and initial exploration. Our journey begins by importing the initial libraries, NumPy for numerical operations, pandas for data manipulations. Then we load our laptop data.csv file into a pandas data frame, which we will call df. A quick peek with df.head gives us our first look at the raw data. So as you can see, we have column like company, type, name, inches, CPU, RAM, memory, GPU, ops, weight, and price. These are the raw ingredients we will be working with. Each row represent a unique laptop and these columns describe its specifications. To get a better understanding of our dataset dimension and data type, we use df.shape and df.info. df.shape tells us the number of rows and column. In our case, we have 1303 entries and 12 columns, which is a decent size for our analysis. df.info is incredibly useful. It provides a summary of our data frame, including the number of known null value for each column and their respective data type. This helps us quickly spot any missing data or columns that might be in the wrong format, like numbers stored as text. Before we proceed, it's critical to check for data quality issues. We use df.duplicated.sum to count any duplicate rows and df.isnull.sum to identify missing values. Thankfully, in this dataset, we found no duplicate and no missing values, which is a great starting point. This means our data is relatively clean, saving us some initial headache. Secondly, data cleaning and type conversion. The first cleaning step involved dropping the unnamed zero column. This column is typically an auto-generated index from the CSV file and does not provide any meaningful information for our model. Using in place true ensure the change is applied directly to our data frame. Next, we tackle the RAM and weight column. Currently, they contain units like GB and kg, making the string object. To perform numerical operation, we need to remove these units. We use the str replace method to strip GB from the RAM column and kg from the weight column. Now, if you look at df head again, you will see that GB and kg are gone and leaving just the numerical value. This is a critical step before converting their data types. With the unit removed, we can now convert these columns to their appropriate numerical types. We convert RAM to int32 and weight to float32. This ensures they are treated as numerical feature ready for mathematical operation and model training. Our final df.info column confirms that our RAM and weight column are now correctly recognized as numerical data type. This cleaning process is vital for the accuracy and efficiency of our machine learning models. And third, EDA. EDA stands for Exploratory Data Analysis. Now that our data is cleaned, let's move on to the exploratory data analysis or EDA. This is where we visualize our data to uncover pattern, relationship, and insight. We start by examining the distribution of our target variable price using a disk plot from the Seaborn library. So this plot shows us how laptop prices are distributed across our dataset. We can observe if the prices are normally distributed, skewed, or if there are outlines. Understanding this distribution is important for choosing the right modeling techniques later now. Next, let's look at the company column. We use value counts to see the market share of each laptop brand and then a bar plot to visualize the average price for each company. This helps us understand which brands are more prevalently and how their pricing strategy compare. As you can see, some companies dominate the market while others have a smaller presence. More interestingly, we can observe how the average price varies significantly across different brands. For instance, Apple laptops tend to have a higher average price compared to others. Similarly, we analyze the type name column which describe the type of laptop such as notebook, ultra notebook or gaming. We visualize their distribution and average price to see if certain laptop type command higher price or more common in the dataset. This gives us insight into the popularity and pricing of different laptop category. For example, gaming laptop might have a higher average price due to their specialized hardware. Finally, for our initial ADA, we examined the inches column representing screen size. We use a disk plot to see its distribution and a scatter plot to observe its relationship and price. While screen size might seem directly related to price, the scatter plot helps us confirm if there is a clean correlation or something more complex. Interestingly, while there is a range of screen sizes, the direct correlation with price is always straightforward. This is where feature engineering comes in, allowing us to extract more meaningful information. Fourth, feature engineering screen resolution. The screen resolution column is rich with information, but it's currently a string. Let's break it down. First, value counts show us the variety of resolution and panel types. Notice how some entries include touchscreen or IPS panel. These are valuable features that can significantly impact a laptop price and user experience. We will extract them as separately binary feature. We create two new columns, touchscreen and IPS. We use a lambda function to check if the touchscreen or IPS keyword are present in the screen resolution string. If they are, we assign a 1, otherwise a 0. This transforms categorical text into numerical binary features. So a quick TF sample 5 shows our data frame now includes these new insightly columns. This is how we start to make our data more machine learning friendly. We can then visualize distribution of touchscreen laptop and their average price. As expected, laptop with touchscreen often command a higher price. Similarly, we analyze the IPS panel feature. IPS display offer better viewing angles and color accuracy, which can also influence price. Beyond binary feature, we also want the actual resolution number. We split the screen resolution string by x to get the x and y resolution. The expand is equal true. Argument create new column directly. Now we have xres and yres as a separate column. However, they might still contain some text or be of object type. We clean xres by removing commas and extracting only the numerical part using regular expression. Then we convert both xres and yres to integer type. This ensures we have pure numerical resolution value. Here a cool one. We calculate pixel per inch or PPI. This is a more meaningful metric for screen clarity than just resolution. We use the Pythagorean theorem to find the diagonal resolution and then divide by the screen size in inches. This new PPI feature is a powerful indicator of display quality. Let's check the correlation of our new feature with price. We will notice that PPI has a much stronger correlation with price than inches alone, highlighting the value of its engineered feature. Finally, we drop the original screen resolution inches, xres and yres column. Their information is now encapsulated in our new, more informative feature like touchscreen, IPS and PPI. This keeps our data frame clean and focused. Fifth, feature engineering CPU and memory. Moving on to the heart of the laptop, the CPU. The CPU column initially has a very high number of unique values. As shown by value counts, this high cardinality can be problematic for machine learning models. So we have 118 unique CPU types. This is too many for effective modeling. We need to simplify this feature. Now to simplify, we first extract the main CPU name like int core i5 by taking the first three words. Then we define a custom function, fetch processor to categorize these into broad groups. Intercore i3, intercore i5, intercore i7, other inter-process and AMD processor. This is significantly reduced the number of unique categories while retaining critical information. Now our data frame has a new CPU brand column which is much cleaner and more useful for our model. Next, let's tackle memory. Similarly to CPU, the CPU column is complex, containing information about both storage type, SSD, HDD, and size, often combined value counts. Reveal the various combination. We see combination like 128 GB SSD plus 1 TB HDD. we need to separate these into distinct features. So this is a multi-step process. First, we clean the string by removing GB and converting TB to 00 for consistency. Then we split integers that have a plus sign to separate different storage components. For each component, we identify if it's an HDD, STD, hybrid, or flash storage. Finally, we extract the numerical size for each type and create dedicated column for HDD, STD, hybrid, and flash storage. So after successfully extracting all the journal memory information to the separate column, we can safely drop the original memory column. Our data frame is now much more organized and ready for molding. So, and there you have it. In the first part of our laptop price prediction project, we have successfully performed theoretical data exploration, cleaning, and feature engineering step. We have transferred raw, messy data into clean, structured, and highly informative feature for CPU memory and screen resolution. These engineered features are the backbone of any robust machine learning model. They provide a much cleaner picture to our algorithm, leading to better prediction. In our next video, we will deep into our advanced feature engineering model section and finally building our predict model. If you found this video helpful, please give it a thumbs up, subscribe to the channel for more data science content, and hit that notification bell so you don't miss part 2. Thanks for watching.